Okay, here we are. Welcome back. It is the final stream of 2024. I will be your wonderful host for tonight, or semi-wonderful, depending on how we go. Co-wonderful. I'm Agent Ultra. On this channel, I hack on projects in the programming language called Haskell. We do some functional programming just to show that smooth-brain, practical little hacker like me can still take advantage of it and build cool stuff and have fun. Yeah, so let's get into it. We're going to be just like hanging out and probably just doing advent of code. Reminiscing on the projects we've done this year and just answering questions and talking and chatting and having a little fun. So if you got any questions or you want to know what I'm up to or you want to show off any of your projects or talk about anything related to that, you know, let's see it. Let's talk about it. Let's do it. Let's get into the problem. I'm working on day 12 today. We're going to work on the garden groups. All right, so why not search for the chief historian near the gardener and his massive farm? There's plenty of food, so the historians grab something to eat while they search. By the way, if you haven't solved this one yet and you don't want to know the solution, it's okay if you jump out. It's all good. Hey, Tardus, what's up? You just did it? Cool. So, try not to... It's okay if you spoil by accident. I'm not going to be too upset, but hints are okay, you know? Or maybe we can, like, you know, check out your solution after if I manage to solve this one on the stream. You know, see how things go. I love reading other people's solutions, too. Like, when I finish them, I go look at everyone else's and be like, oh, wow. Because, like, some of the solutions are pretty neat. I was watching Ericto earlier on YouTube, and he's been doing them. He's like a competitive programmer, so he does them in a completely different style than I do them. I've been taking it super chill, and when I write these, I usually write them like slow and steady. I write unit tests and the whole 9 yards as if I'm writing software normally. So yeah, I'm not much of a competitive programmer, although like it's fun to try once in a while. Anyhoozle. We're about to settle near a complex arrangement of garden plots. Oh, that sounds familiar. I used to grow veggies in a community garden. When some elves ask if you can lend a hand, they'd like to set up fences around each region of garden plots. But they can't figure out how much fence they need to order or how much it will cost. They hand you a map of the garden plots. Another grid-based one. Cool, as you can probably tell from there. Each garden plot grows only a single type of plant and is indicated by a single letter on your map, where multiple garden plots are growing the same type of plant and are touching horizontally or vertically. Okay, so not diagonals. They form a region. Cool. For example, so all those A's. Cool, cool. Well, some of my favorite board games, I play a lot of board games, by the way. Some of those are like area control games, and this is like a very common sort of pattern you see in those. So regions, interconnected orthogonally. So this 4x4 arrangement includes garden plots growing 5 different types of plants, labeled A, B, C, D, and E, each grouped in their own region. In order to accurately calculate the cost of the fence around a single region, you need to know that region's area and perimeter. Okay, I think I know where this is going. The area of a region is simply the number of plots the region contains. Simple enough. Each garden plot is a square and so has 4 sides. The perimeter of a region is the number of sides of garden plots in the region that do not touch another garden plot in the same region. So that's very specific, but this diagram kind of shows, I think, what we need to count. So this would be like 1, 2, 3, 4, 5, 6, another 4, so 10. All right, this would be 3, 3, and 2, so it'd be 8. All right, this one would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This one would be just straight 4. Pretty straightforward. I think we got this. Plants of the same type can appear in multiple separate regions. Okay, that was going to be my next question. And regions can even appear within other regions. For example, we've got X, X, so it's 4 separate regions here. And then one, and I guess the O's all surrounding them is another region. That's 5 regions altogether. Okay, which means that O region is going to have quite the large perimeter there. The 4 X regions have 1 perimeter 4, and the region containing 21 O plants is more complicated. In addition to its outer edge, contributing 20, the boundary region with each X contributes an additional 4, for a total of 36, yeah. Okay, and due to modern business practices, the price of a fence required for the region is found by multiplying that region's area by its perimeter, probably summing them all up to get the total price of everything, right? Yeah. Sounds good. Okay, so there's a larger example. Cool. Okay, so it looks to me like what we're going to need to do is we're going to have... Yeah, let's get the sample input as a small version of this, and then we'll get the main to write some tests with if we need it. And then we'll get my main input. But it looks like it's going to be like some kind of flood fill algorithm, and keeping track of like which ones we've filled and which ones we haven't yet, that kind of thing. Okay, Advent data 2024 day 12. I'll just call this one sample. One of the things I've been wanting to do actually with this admin project is to like change the structure a little bit. Right now I've got it all set up so that all my solutions for all the days are like in one single binary. I either want to split them out into separate binaries or introduce like a CLI front end to it so I can just test with one at a time. Because some of them are a little bit slow. Not well optimized. And then when I want to get to like the answers for the later ones, I gotta like comment out a bunch that are slow and like kind of annoying. Anyways. So there we go. We got our data. Let's go to a source. Advent 2024. Day 12. Okay, we'll do a little input action. 24, day 12, dot input. Where? I have some, since there's been quite a bit of grids, I have some code from prior days. Day 11 a grid. I didn't do day, did I? I thought I did day 11. Oh, I should probably update my code. Yeah, there we go. I haven't updated on this machine in a while. -R, rebase, pull. There we go. On stage, yeah. Stash. Cool. Apply that one, kill it. Cool. Yes. Okay, and then what? Where did it go? I'm jumping around here, and I see him get ahead of things here. What did I... Oh, pulled. Oh, I did pull. Oh, okay, get saying like no. Okay, that's no problem. Get rid of that, get rid of that. There we go. Okay. Back in action here. wasn't it. Day 10 grid. Yeah. I should probably extract this out into a function, so I can seem to be doing it a lot this year. Day 12 input. Yep. Wrong key, sorry. Straighten up here. Pop that over there. Good. Okay, not a trail map this time. Grid of cars. I'm not going to put a new type wrapper on it this time. We don't need to... Oh, no, we can just pure that. Car grid. Saw. Yeah, stylistically, I'm getting like some suggestions here. Yes. Probably just get rid of that whole bit. Okay, we happy now? Let's go to part 1. Let's get 2024, day 12 input. Let's get a grid. Get input. Yeah, we're gonna go data. 2024, day 12 dash sample for now. Just gonna print that out. Oh, it's not in IO. Here, I'll get the raw. Pop that there. Raw there. Import data.text.io. That's T. I want that qualified. And this just becomes a let, not a binding. Okay, let's get our builder going. Use file launch. Uh-oh, bad merge. Bad merge. What did I do? Ooh, Oh, what file is that? Event source. 4, 89. I think that was from last week when I first started the stream and had some technical difficulties there. I think we went with file. So we'll go with variant A there. This is both. It's gonna have to recompute the hash here because I don't know. Just get it to rebuild. Okay. Yeah, then wants to rebuild a bunch of things. That's all fine and dandy. You do your thing. We'll just move ahead a little bit. Okay, so the first thing I want to do with this grid is I want to get a map of the ones that have not been painted yet, I think. I think that's what we want. Because what I'm thinking is that, well, initially that map would be like all unvisited. So we pick one. Say the first one, doesn't matter. Right? And it's this R1. It just happens to be 0, 0. And then once we get that one, it's not been painted yet. So we start what's called a flood fill algorithm. The flood fill is pretty straightforward in its most basic form. It'll just go through and like paint all of these. Right? And as we're painting them, it's going to find all the R's. And as we're painting them, what I would think we should do is basically do our perimeter detection while we're doing that, because we're going to visit all the cells that are R's, that are same, and that means we're eventually going to bump all these R's. We're going to bump this R, and anywhere we detect like a neighbor that isn't an R, we know we're on a perimeter, so we can increase our perimeter count as we go with our flood fill. And then we also have the area as well while we're going along, and that way we can get both pieces of data as we're going along, right? And then we basically fill in each R that we visit in our flood fill. We mark it as visited in our visited map, and then when we go to pick our next one on the next iteration until all are visited, basically, and then we stop. And I think that's how that'll work. Alright, so we got our grid, we got that. We got it compiled. A little run. We're not in the right directory for it, so we can't find the data file. Let's see. Fair poop. Okay, cool. I think I printed out our little grid there. Yeah, sweet. It's gotta have that. Okay, part one, go over here. Duplicate code, but whatever. Okay, so visited. Let's make that a map. Let's put us in, say, a function answer. And I don't know what type it's going to have right now, but it's going to take our grid. And it's got to output an int. So there. Okay. So first things first, we need visited. That's going to be an empty. An empty of what? An empty of a map. Probably coordinates to bool. Sorry, grid card? Yeah, grid. We gotta import that. Probably gonna need it, so we'll import qualified now. Cool. Okay, so we got our hole here. We have a grid card int. We have our visited map. Okay, so now what we need to do is we need to pick one from visited. Or no, we need to load Actually, we need to load that up. That map up. Make visited from our grid. Okay. Why don't we just go ahead and fill that one in? Okay, so I have in my grid module this to do the indices. I'll just do this point free, maybe. We'll do map.from list. Yeah, map.from list, grid.indices with we'll be able to do that point 3 because I want to be able to do that. Oh, yeah, I should be able to actually. Hang on. Getting a little clever. Because I want to zip that together. But I want the second list to be the booleans. Or it could be repeat or false. I'm going to flip that. Does that work? It's just not a scope. Qualified data. Cool. Cool. All right, so we have our visited map now. We got to pick one from it. I'll pick an unvisited. Yeah, gotta keep it at a reduce. Always be reducing. Right, so we want to get the map elements. No, the association list. And from the association list, we want to filter for. This is going to turn maybe into int. All right, we want to filter for the second, not the second. All right, so the ones that are false is the ones we want to keep, and we want to take the first of that. So we'll do list to maybe. What's my problem here? Oh, first. Sorry. No. No, second. I mistyped something. int bool. Let me pop a hole in there. Oh, okay, yeah. Okay. We're missing a function. That's right. So we need the first. Okay. That's how we pick from it. All right, so now we're gonna have to recur over visited until visited is visited. Until we're done. So all done. Take our map, int bool. Return bool. Yeah, and this is just map elements all. Oh, you want a function there, and. There we go, that's what I meant. Okay. So now we could define our recursive function. Go. So we'll give our visited map, our grid, and yeah. Do we want to do recursively? Or do we want to do a state? Let's just keep it simple for now. If we need state, we'll pull it in. Right, our grid of var, and we're turning it int. Visitors, grid, and such that all done is our base case. Then we have to return something there. I think we're going to need state, because we're going to be, as we're doing this, we're going to be keeping track of, like I was saying there earlier, some variables like the perimeter count and stuff for the region that we're currently looking at. You know, all that stuff. Yeah. I don't think we have enough information here in this type to be able to do that. Right, so region search. Okay, so in our region search, we're going to need the visited region, or the visited things. Oh, so I'm gonna eventually pull up this variable into the region search, but for now let's just define it. It's gonna be our map, int to bool. What else we need? We need our grid. That's going to be our grid of chars. And Let's see, we only care about the sum of all of these things. But while we're looking at a region, we're going to need some data. And while we're doing our flood fill, I might be able to treat that as a separate kind of sub problem. So let's keep our region cost as an int. Our total cost. Here. Yeah, I don't know. Okay, so then we just the eval state with our region search and our initial stage. Search. Region search. Visited. And our grid, total cost 0. So search will have type, state, region search. I guess it wants an int, probably, because it turns type. Yeah. So we might be able to actually not really keep the running total cost, just have the grid and visited. In which case this would actually be more like a reader. Except, no, visited might change, will probably change actually after each run of our flood fill algorithm, I suppose. What would search look like? Well, search will probably check for our end condition. Well, maybe we will need our total, because we could put our some value here. Else, something else, right? Total sum's fine. Just get it like that. Or it's a bit awkward, but works. Otherwise, we're not done yet, so we have to do our flood fill. Have to pick an element from our grid. Pick an unvisited element from our visited map. And then we can do our flood fill on that part. That's what it would look like, right? It would be X say. Pick from these. And then our flood fill would return. What would it return? It would need to return the area, the perimeter size, and the updated visitor map that we can put back into the state, I guess. Give us a cost, a new visited map. We will call it flood fill. And it will get the grid out. The visitors and the position. What we got from pick. Pick is going to return maybe. So let's just throw like an assertion there. Okay, and assuming we get all that back, then we just update our state. Such that the visited equals v's prime and the total sum equals the... I'm already wanting MTL, or yeah, MTL lenses here. So let me go pull those in. Lens.micro, lens.micro.mtl. Okay, and then we can do this nice and easily with visited. We just set that to V's prime and total sum to plus equal. I think it's just plus equal, actually, just like that. Plus equal cost. All right, we haven't defined flood fill yet. Give us a second. Prepare the car, map, and bool, and int to go on, returning and a map int to bool. Make sure that's okay. Oh, that's gotta be a state. Actually, I won't have to pass those in as parameters if I just do it on the state, actually. Yeah. I just have to give it the X that we picked, I guess. which case, it doesn't even have to return those because it'll update it itself. The problem here... I meant from just remember that. Yeah, my prelude doesn't want me to use that. Okay, fine. Somewhat safe code, try and protect me. In this case it'll be ID, in this case it'll just be error. What? Yeah, we need overloaded strings. I should probably just add that in my the ball file, to be honest. A lot of language extensions I use these days just by default. Error success dev. What's up, Error Success Dev? Okay. This is Haskell, by the way. Haskell, the notorious functional programming language that's completely useless and very impractical. But I like to have fun with, and you know, I get paid to do it too during the day and work on a million some odd line code base written in it. Very impractical though. What does functional mean? That's a good question. So I work at like a fintech company. We do banking services type stuff. It's called Mercury. Pretty cool place. And functional languages, geez. I don't know. There's the academic answer, which is like it's the primary means of evaluating a program is by applying functions to arguments and defining new functions. That's it. Yeah, it's often, the definition is often given in like contrast to other programming languages that are not like that. Like C or anything like that, if you're familiar with those. Yeah. It's hard to explain, to be honest. So like in a C program, you kind of have like instructions that start, you have an instruction counter, and like your program, you can kind of read it from top to bottom as like a procedure. You know, like at this step, this. And then you have control statements, like if something is true, go to this branch, if not, go to that branch. You don't really have that in Haskell so much. It just uses functions and applies those functions to the arguments, and that's like the entire program is one giant function. It's kind of a weird way to program, but you can do it. You can do it in other languages. You can do it functional programming in C. You can do it in JavaScript. It's just not as pleasant as it is in Haskell. Yeah. Except it is fully compiled to machine code, and produces pretty good code. The runtime is smallish. It's garbage collected, but has a pretty good garbage collector and really excellent concurrency. Primitives and libraries. I can't stress enough how good they are. There's another, on top of the function stuff that Haskell does, another kind of infamous feature of it is that everything's immutable by default. So you don't have like an assignment operator that changes a variable over time. Everything's immutable. And when it comes to concurrency, that's actually really useful, it turns out, in order to avoid a lot of situations like race conditions and deadlocks and stuff, which you can still get, but they're much easier to detect and much easier to avoid when you have that. So, yeah, and lazy evaluations come in handy, even in advent of code, actually, in some of these problems I've used. It's very common to, like, define the algorithm such that it generates all the possible solutions. And it looks like it would be inefficient if you were in a strictly evaluated language. But since it's lazy, it only picks from that the ones that are the answers, which is kind of cool. I mean, in the worst case, you'll still get worst case behavior, but usually if you got the answer, you'll get it pretty quickly, which is nice. So you end up writing quite a bit less code in that, in some of those kinds of problems. Because you don't have to deal with control structures and control flow and that's all good. I know C and I know like a little bit of C# too from osmosis. Mostly I haven't really done a whole lot of it, except maybe like some game engines that use it. Unity and such come to mind. Yeah, okay, so no instance is string grid car wrong right. Oh, alright, that doesn't need to be a string. Just put error on that. Boom. Okay, so we just have to fill in flood fill. PowerShell, nice. I use it, but I don't write a whole lot in it. I usually mainly use this desktop here you're looking at as on a Windows machine. That's what I use for media stuff, a bit of gaming every now and again. And, yeah. But I mostly develop on Linux and use Linux for the most part. Except when it comes to media stuff. Hardware drivers just aren't there for a lot of the stuff that I use. Just the way it is. But anyways, flood fill. Okay, so in order to do a flood fill, we need a queue. We need a queue. Queue data structure. Something double-ended. I mean, we could possibly just, use a list. Maybe, like a linked list. Because we'll only be if and use the stack approach. I don't think it really matters a whole lot. Let's just use the stack approach and not bring in another dependency. Let's see if that'll probably work. Okay, so we're going to start with a queue that's going to be contain just X. Going to be a list of locations, and it's also going to be a state, region search, int. Okay. So in order to do the flood fill now, the kind of general gist of it is that we need a neighborhood function that looks at a particular location in our map and then finds all of those spaces that we can add potentially to our flood. Alright, so if we picked this R here, right, we don't do diagonals. I believe it's all orthogonal here, so that's only up, down, left, and right. So we go down here, 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 and here. And we only care about the ones that are ours, those ones we're filling, in this case. So I think our first stop is to pop our element off of our stack. Well, our base case, actually, let's just do that. That's where the stack is empty. We have to return something there. Otherwise, we pop off the stack there, some X, and we do something with that. Okay, now in our base case, what are we going to return? We could probably return... not the total sum. We're counting, as we go through the flood fill, we're going to be counting the perimeter and the area. So we need a sum to track that somewhere. A to reduce. So we're going to do a flood fill algorithm here. That's going to be a stack of nodes to visit from our map. And the general algorithm, it goes like this, where you have an initial stack of your like first pixel you're going to visit. Call it like Q or S for stack. All right, you're going to pop an element off that stack. You're going to pop off of S, and you're going to get the neighbors. And you're going to push those onto the end of the stack. Right, onto S. And then you're going to mark, of those ends, you're going to mark the ones in your visited. And then you repeat until S is empty. Yeah, it's because you're going to be pushing on to the stack as you recurse. Right, you can do it with a stack, and then you can do it with a queue as well. Not a huge difference. It ends up filling the same. The only difference really is like the way it progresses through the grid. Right, so we get... What are we going to return in the base case, though? We're going to need some extra state to keep track of while we do this. So our current area and our current perimeter. And we'll just type it out. Now return pure Area, I think they wanted area times perimeter. Yes, 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 I am. Here as well. Okay, that makes sense. Now for this hole, we need to recur, so we got to do our getting our neighbors. Neighbors of X in grid. So we'll get our grid. I don't think I have anything bound to the scope for that, so gets grid. Yeah. Okay. And then we need to do our check. So once we have all the neighbors, we know our current position, we know the position of all the neighbors in our grid. All right, so we'll have like one above here to the left, right, down, or north, east, south, and west of R here. And we'll need to look in the grid for each of those. So we'll have to get all of them. Maybe our neighbors function could return that helpfully as an association list. Yeah, and all we have to do is add them to our visited. Oh no, we need to check. We need to return all of them. I'm not, sorry, I'm skipping ahead of my head here a little bit. I'm not explaining on stream. So the neighbors function is going to return all 4, regardless. And it's not going to do any filtering. Because we need to be able to do that detection on the edges of the perimeter. Or marking, not only marking visited, but so we can increment the perimeter and the and we'll also increment the area count no matter what, as long as we're on a R. And then the case where, and then we only add the like ones as the current one from our neighbors into the stack. Yeah. Okay, so it's quite a bit that we got to go through in order to get there, but let's do it one step at a time here. So let's get the... So if this returns as an association list, like neighbors could reasonably take a int a grid of char and return the association list of int, and chars. Now, assuming we have that, then we can implement that, which I'm pretty sure we can. That means that in order to mark off, increment our perimeter count, our next perimeter value will be the count of neighbors that are not our current cell value. So we need our cell value. We'll call it C. Don't need to do that. Yeah, don't need to bind it there that way. let's bind it in the lets. Grid get at x. Alright, so we count the nothings, because this will return a maybe, so that means it's outside the grid. So we'll count those, and we'll count the neighbors that aren't equal to C's value, that aren't equal to C. Meter plus the sum of will this be the sum of filter something in neighbors? Call it, we'll give it, call it perimeter cell. Oh, is perimeter cell. Make it less confusing. So I want a function called isPerimeterCell that filters our association list of int cars. We're going to need to compare it to C, so we'll have to pass that in as well. isPerimeterCell. I spelled it like that. And that's just going to be filter such that we don't really care about the location. Oh, This is why you need to structure your types right. So neighbors, if we remember check our grid, if we get an edge one, that's going to have a nothing in it. So it's not going to be directly an association. It's going to be an association list of maybes. There we go. And that means we're going to get maybes here. So we care about that it's is, and we want to keep it if it's is nothing S or S is not equal to C. So we're only keeping the cells from the neighbors if they're equal to the current cell that we're looking at, or if it's a perimeter cell, like a sort of external cell, like outside the map. So we filter all of those, and then it's not sum, it's length. Not the most efficient way of doing it, but I'm not too worried about that right now. Turns out to be... This is going to be small. It's going to be like 4 elements at most, so it'll probably be fine. Yeah, do block. Okay, so we're still working here. Okay, so that's the next value for perimeter. Area. That's going to be just area plus 1. All right, and our stack. Our next value for stack is going to be the remaining neighbors. So we're going to take the cat babies to get rid of all the neighbors of ends. And of those, we just need the second element. Or first. Okay. Then we need to mutate the visited cells, the visited map. So we'll do visited. I think it's like that, little squiggly woodabity boops. So shorten it in a sec. And all we're going to do here is, what's it called? Modify with, I think I used it in day 11's stone solution. Not from list. Yeah, from list with. That constructs a new one. No. I want to modify the list, the map. Close you. Close you. What's the function? Data.map. Script. I'm looking for like some kind of fold into the map. Fold R with key. I don't know. No, more like an insert. Probably just use modify or alter and map over it. There's probably like some clever function in here for it though. Or just update. Yeah, or just update. Because all we're going to do is basically, for each of those locations of the neighbors that are in the map, we're going to... Yeah, so we will need alter, because neighbors might have, unless we filter it out, it's going to have keys in there we don't want. So boom, alter some function over the... I'm going to just use plain old fold L, something with V as our starting map over ends. And I'm forgetting the name of the operator. Lens.micro. MTL. View. Scoobity boops, scoobity boops. Oh, it's just percent equals. Nice. Okay, sweet. In the center. Ew. Ew. So my fold function here now. This one. Update visited. Update visited. What's the type of this? Tell me, Haskell. Oh, somewhere in there, it's not highlighting it for me because there's other type errors to work on here. Right. Yes, here is a maybe. So we need to do something about that. Can I lift this equality operator, this equation into the it's also going to be a pair. That's tricky. This could be... This is nothing. Let's use pattern matching here for this. So maybe an int char cool cell C and X there. Nothing. Ooh. That equals. And a perimeter cell C with just X. C is equal to. Sorry, not equal to X. Oh, okay. Haskell saved me from being a dingus. It is actually just this. I was not paying attention. Ding. Ding. Us. There we go. Okay, so the other two are fine. Okay, so let's see. Visited. Date visited. Yeah. So you don't know the type of that yet, which is why I'm getting that all. The type of this. Could be. This one, I think, actually. Yeah. But the inference can't figure out the type for me on V0 there. But B0 is going to be just int. I believe. What's the problem? Yeah. State region search. Can match the type region search with. And go. I think I got the stack, the perimeter. It's gonna get a maybe again from grid get at there. Do from just again. I'm pretty sure that's gonna be checked and fine. And if it isn't, we'll get an exception. Of course, it's not gonna let me do that. There. Okay. Better? Better. Everything's better. So far. So good. Okay, unexpected do block and function application. That is unexpected. No? Because of this hole? Yeah. Let's pop a function in there. Put the hole in here. What do you think the type is? Why isn't that working? That's so weird. Visited, yeah. Oh, because I haven't generated the lenses for it. That's why. Region search. Probably gonna need template Haskell. I might go to TH. There we go. Import lens.micro.template Haskell TH. This will just generate the lenses for us, so I have to write them out by hand. I can't believe I forgot that part. Silly me. And then I'm gonna get a bunch of name errors, aren't I? That's okay. We have getters for that. Good old view, preview, and use. That's what I was expecting. Perfect. Okay. And then update visited should fit in that hole. Quite. Why do we... Right. Let's take our map first. Int bool to a map int bool. Wonderful. V and nothing. We don't have to do any alterations. V. Otherwise, we're going to be just. We only really care about the position of the key. Oh, when we're updating the visited, we're going to need to not update the ones that aren't the ones we're trying to fill. So if one of those neighbors, for example, is, and we're filling in R, and one of those neighbors is I, we actually don't want to fill I in, we want to ignore it. Just like when we were counting in perimeter cell. That just means I'm going to put car here. Ignore it in that case. Here we need it. M. Yeah, such that C equals M. Then we will update the visited map. And we'll just do const just true. And a key. Right, and then in the other case, we can ignore C, we can just want V, we can ignore this. Just return V. Quite done yet, though. See. There we go. Okay, now we just have we're back to our hole now. Okay, so we've got most of our stuff updated. We've updated the visitors now. What else do we need to do? We need to put onto the stack and then repeat. Alright, so all we need to do is call go with our new stack, our area calculation, and our new perimeter calculation. Okay, did we not use grid? Oh, just shadows. Okay. Can I call it G? Used X is the problem with X. Oh, that's shadows. Let's call them Y and Y's then. Y and Y there, and Y's. So our stack needs to We need to grow our stack with our Ys. I guess we're gonna grow it that way. Yeah, then we just need to define neighbors. I'm missing that. Pretty straightforward, hopefully. Let's go ahead, and then I think we'll actually be done with part 1. Okay. Okay, let's go to grid. Now we're going to get at the value A, and then we'll just fmap onto that with our coordinate. We have to get all of the directions. So, do something there. So we're going to get D for each in grid.directions first. Yeah, something like that. Actually, this might even be just a one-liner. Get at G, and we're going to do grid.offset. D. And that's going to be, no, not quite done. C plus that. Also comes per grid. And this hole is car to int car. So that'll be C, and we'll go also want that. Let's just keep going ugly. We'll be fine. That and C. Probably I need a parenthesis. What do we got here? I had misunderstood that. Suggestion. Oh, tuple sections. Yeah, that's a little clever. Not a huge fan of tuple sections. But it would make this shorter. Okay, I think we're close to compiling. Looks like we're good to go there. Cool. Some little cleanups to do here. What else? We didn't use G. Probably get rid of that. Okay. Right. Got our answer. Let's see if we get something reasonable. Just for our test input at the moment. No word if this is going to be even remotely fast enough. I have a feeling that our flood stack is going to be no bueno. Looks like it. Or we're getting into an infinite loop somewhere. Okay. What do we need here? We need to... Well, the thing that I'm worried is the slow part. Is where we are growing our stack as a list here, because... Yeah, we're popping off here pretty easily off the head, but... We're actually, when we grow the stack, we're growing like multiple... We're adding multiple things at once, and so we're using list concatenation, which... If the stack is big... That could be the thing. Wise isn't going to be huge in this case. Or Wise could actually grow to be quite large as well. Stack prime is going to be pretty small. So... The other thing is that I could be missing... some key terminating condition here. Probably is. This almost feels like a festive song. What's this doing on the playlist? Oh, but it looks like we're running out of time. Oh no. Oh man. Okay. What can we do here? Did I get the flood fill algorithm wrong? my gosh, this song. Sorry, I can't. It's gotta be something else here. Pause. The choir was getting me. Okay, it's probably the flood fill, I would say. Since it's the last one of the year, we'll go a little later than usual. But not too much. Okay, so when we got there, I'm just gonna... Every time we enter... I just want to check out our stack. Is it that our stack's growing infinitely, never ending, or is it just getting too big? And it's getting, the concatenations are getting too slow, are slowing us down. It shouldn't be, because like the example is small. So I'm imagining it's just, getting into a loop somewhere. All right, proving that we always consume from the stack faster than we add things to it. That's a little bit trickier here. Mainly because of neighbors and stuff. So, boom. Seems like we're just growing and growing and growing. Nine one 80 92 81 80 92 81 80 92 81 80 92 81 80 92 81 80 92 81 80 92 81 80. Yeah. That's a lot of the same stuff over and over again. Okay, yeah, that might mean that... So why is this decreasing? Stack is what we're prepending first, so stack prime is growing. It's got to be, how is stack growing like that? So take stack prime, be the neighbors there, and then we go and recur. This is not all the neighbors, just only the ones that are in bounds. Well, we do need to filter out. I think I see what's happening. Cat maybes is only filtering out the neighbors that are outside of the bounds of the grid. We still need to filter out the ones that are also outside the bounds of like our region that we're looking at. So like the not of this function. universal. Let's see. Oh, because the cat maybe's off. Let's just write it as internal cell. It'll be int and char. Bool. Reduce sweet update visited, but do we ever check if something is already visited? I'm pretty lost on what it is, honestly. Ah, yeah. You caught it. Cool. Yeah, we do set visited. I think it's the neighbors, is that it's also it's adding cells that we don't want to fill to the stack, basically. So, let's see, and we don't care about the first element, we just care about char. And so C equals X. Okay, pow. Stack's growing. Okay, we're still getting the same issue though, just different numbers. 120. Let's look up blood fill algorithm. So we start off, this is basically kind of what we're doing, except we're not going to use diagonals like in this one, just in the up and downs here. Alright, so you start with our seed, S, our start, and then we set our current node to visited. We forgot that step. We're doing all of those. And not inside the, yeah, the set. Right. So Q or stack, right? That's Q grows out like that, stack grows like this. Add node to the end of Q. So our current node we're not adding, I don't think. To visited. That's true. So Y we need to add it, we need to update visited with as well. So we'll pause that on there. Okay, let's get an answer. Whoa. Trippy. No, we're still not doing it. Okay, something about our bounds condition is not quite there yet. Okay, so we added ourself to the algorithm. So the current node that we're visiting. Yeah, that's what we do. So that's the current node we're trying to visit. We set it to the head of our queue, or stack. It'll recur. While it's not empty, that's this case here. Set n equal to first element of queue. That's y. Remove the first element from it. If n is inside, means it's already visited. It's not visited. Okay, so in order to generalize the algorithm in the common way, the following descriptions will instead have two routines available. One called inside, which returns true for unfilled points that, by their color, would be inside the filled area. Okay. And one called set, which fills a pixel. Or node. Any node that has set called on it must then no longer be inside. Oh, okay, I see what we're doing. We're infinitely visiting the interior of our thing. So we need to finish the fill at some point. That's what we're missing here. So not only visited, like over the whole map. No, actually, where are we doing that? We are setting visited with ourself. Yeah, all the internal cells that we get from neighbors, the neighbors function. We're setting those to visited. Yeah, and then we're adding them onto the stack. Yeah, so we are visiting them indefinitely. And that kind of makes sense to why the output in our output here is like repeating the same grouping of coordinates in our grid. I think that explains it. So we need another filter out of those neighbors for our stack prime to filter out from the ones we've visited currently already. There's not only just like the visited overall, which keeps track of which regions we have already visited. Yeah, okay. Perfect. This is coming together. We're almost there. Okay. So to go back to my plan, since the stack of This is the neighbors we're looking at. We want to only paint the ones internally in the region in visited. Because when we, after return from the flood fill, when we go to the next step of our algorithm, all of these are not going to be included in pick. But for the flood fill algorithm, we still need an internal set of visited ones so that we don't keep adding them back to the stack again and visit them constantly. So we need to initialize an empty set when we start there as well, as part of our flood fill. If we need a better data structure than a list, we can do that. I'm just going to try it for now with a list just to see if it works. That'll be a list of intents. Okay, and all that internal there. So filter is internal, then can take the C and internal list. And there we go. And we just add X is not a gnome. Of internal. And we want this to be both be true. Or sorry, not X. Call it P, whatever. Right. I think that makes sense. So we check the coordinate of that internal cell, and if it's not the ones that we visited, then, and it's an internal cell, then that's true. And so we can add that to the stack. Now, hopefully this will filter enough that we actually do finish processing the whole stack and we get to our base case. We're missing, we have another equation here. Oh, I have to add that here. And then a recur. Let's call it the internal. Okay, so then we have to update internal with the ones we actually added. That's the last missing piece. Maybe we're using this part of the equation. parentheses. Something with those neighbor cells. We're going to filter. First of those as well. Now this should be not his internal cell. Unvisited cell. So we get the unvisited internal cells and then is internal cell. Or the rest, I guess. Or can we just add all of neighbors, cat maybes, like NCS to that list? So we take stack prime, no, ends. We do all of ends. Oh, yeah, but we filter the, okay, so yeah, maybe we could just do internal and NCS. Which is map first. I don't think we need that one. There we go. Let's see if we got it, folks. Probably not. We'll see. Ah, it's too low. Oh well. But we got it kind of working at least. The flood fill part. All right, that's our stack that we visited. Yeah, that's what I like about, you know, the good parts of AOC. You know, I haven't been like super up on like doing each puzzle each day because I just don't have the time for it. As you can see, like I'm not like a super speedy coder. At least not when I'm using Haskell. And I mean, just in general, I just don't do it. So like if it takes me more than a couple hours at a day, then I generally fall behind and whatever. But I just enjoy trying them out because you learn something by doing them. Right, so I think this does kind of line up to our grid a little bit. Let's just kind of compare it to our sample. So we pick 0, 0 initially, and then we add 1, 0 and 0, 1 to the stack. That makes sense. From there, 2, 0, 2, 0, oh yeah, 1, 1, Yeah, 0, 0, and 0, 1 are still on the stack. Because we grow it out. And then we add 3, 0. There you go. And then we add 3, 1. And at our peak, we also add 4, 2. 0, 1, 2, 3, 4, 0, 1, 2. Yeah, that one. And we should get to 0, 1, 2, 3, 0, 1, 2, 3. A Y3 somewhere. Yeah, 2, 3. Yeah, so it is flood filling, which is good. I'm probably just off on the area and perimeter counts as we're doing the recur. Something like that. No, I know what it is. Ha! This is only doing one flood fill. It's doing one region. That's why it's only 200. Oh, for Christ. Hey, tech support, what's going on? I gotta ban this person here. Get out. Anyhow, how's going tech support? What's up? We're nearing the end of the stream here. I'm just like Yeah, I was saying that earlier. Like usually I don't think I've ever actually finished a whole year because like I'm busy around this time of year. It's just not a great time of year for me to like do programming all day and then come home and do a little bit more at night. Like I do a little bit in and out again, obviously on day 12. I've skipped day 8, done like half of day 9. Oh, dang. Texo, I love Lean 4. That's so cool. That must be a lot of fun. I did a little test of Lean 4 back in the day. Lean for hackers. Oh, jeez. Lean for hackers. Yeah, this page. Which I thought was super fun. Yeah. I should probably update it, you know, it's been a while. But I was trying out Lean 4 and I went and built like a common Unix utility called word count in Lean 4. And it's pretty nice, you know? Yeah, the tooling works great even back then. Hopefully it's gotten better. I was using Lake. Like just worked really well. Lake build's a thing, you know. But I was quite pleased with actually because it generates C code and then you compile the C code. But the C code it generates is pretty cool. Like it is garbage collected in like automatic reference counting is garbage collection. But the way it does ARC is insanely cool. Just check it out if you ever get a chance. Counting immutable beans. Neat stuff. Nice. I'm glad you're having fun with it. Okay, so let's see if I can get the answer here. The reason why it's because it's only doing one flood fill and we're not recurring in the search. Ah. So it looks like our flood fill's working, so I'm going to take the debug trace out from the stack stuff. Nice and fast. Oh no, 0. What? Okay, so it's doing all the flood fills. What are we doing wrong? Oh, we're not modifying total sum. That's what's going wrong. Okay, so when... so flood fill's returning its thing here. So let's bind that. Cost. Then total sum. Plus equals cost. I thought we were doing that somewhere. No. We're just returning it. Okay. Then search again. There we go. That looks like more of a reasonable answer. Come on, let's end on a high note. Ah, no, it's too low again. Ah. Oh, God. Why? No. Oh, where are we going wrong here now? Okay, so our flood fill's working. Are we calculating everything down here properly? No, maybe so? Maybe our perimeter calculation isn't quite right. Our equation here for perimeter prime, our next perimeter, sums together our current perimeter is taking it from neighbors, but is probably not considering the original cell. No, that doesn't make sense, actually. Because we get the neighbors from that original cell, right? The neighbors from Y, the current one we're looking at in the grid. And so that would be like 0, 0. Oh! It's working. It's too low because I'm running it on the sample file. 1930, I think, was what I pasted in there, wasn't it? No, I was too high. Oh no, I'm too high. Well, let's get our actual input. This is why I can't, like, streams after 10 o'clock, man. Like, I'm getting... My spoons are running out. Oh, no. Save page. Oh, I'm on the wrong machine for that. Let's just copy paste. B12. Next. Okay. It sets super early. Like 4:30. Around there. not gonna give it an exact time, but you know, yeah. It's like pitch black by 5 o'clock. A little after that, just done. Darkness. And it's gonna be the darkest night of the year very soon. Yeah, you live in the tropics? That must be nice. That must be different. Well, the closest I've ever been to tropics, I guess, is probably either Florida or Japan. Yeah. And that was wild to me. The humidity was just like, whoa. Pea soup. Yeah, consistently, yeah, I work with some coworkers who live in Alaska, and like they get it. You know, it doesn't set for a long time, and then it sets forever. I don't mind it though. I kind of like it. I like the feeling of the darkest night of the year is pretty neat. Like it gets dark super super early. Doesn't rise for a while, and like you just sit down with a scotch and just relax to the max, you know, share stories, reflect on the year, that kind of stuff, as we are wont to do. Okay, so perimeter prime here. I think I'm getting too high of a number if my day 12 sample is this. Apparently should be getting 1930. Never seen snow. Oh man. I dated this girl once in high school who she came from the Bahamas. I think she lived in the Bahamas and moved here. And her mother is an older lady and had never seen. No, it was not her mother. It was her grandmother I'm thinking of. That's why I'm thinking older lady. It was his grandmother. Had never seen snow. And came to Canada for the first time and saw it. It was like, whoa. I love snow, man. Like, it's because I've lived here my whole life. It's kind of built into me, you know, just as I'm sure the tropics are built into you. But there's some, especially if you go to like the woods in the far north, there's a kind of quiet that settles in when it actually starts snowing, like a big, thick, heavy snow. That kind of like creates this little soft, fuzzy sound bubble around you. And you can hear every once in a while, like little tree, like the trunk of the trees will just like kind of snap a little bit. Their bark will snap, make like a little snapping sound. And a lone animal out there might make a noise, like a wolf or something. It's so peaceful. I love it. Well, that's pretty cool. Seattle, I hear, is very nice from my Seattle working coworkers. I've never been, but I hear it's pretty cool. So we want 1930. 1930, but we're getting like 2000 something, so actually we're going a little too high. Okay, so I'm going to bring back my debug tracing back in. Let's debug. Okay, let's get rid of the recur for now. Get rid of that for now. Actually, let's use that. No, let's get rid of that. go there, and after these bindings. Probably just get the cost out, but I want to see the perimeter calculation of each step here. We get 2, 3, 4, 6, 8, 11, 12, 15, 16, 18, 20. We end up with 260. Which is too much. Because I think it's starting with this region here, this R region. Okay, so if that's not quite right. I'm not gonna do that actually. I want to know what the length of the neighbors is after we filter. Actually, let's yeah, let's take the length for now. Let's just do it after the filter. So it's 0, 0, we should get nothing, nothing. And that should be, yeah, then that comes down to 2. Three. See. Yeah, okay, so... Right, okay, so perimeter prime would be 3... Because... The prior iteration, perimeter would be 2, length of this is 1, making 3. Okay. So the maximum this length this filter should be is 4, obviously, to come from neighbors. We're at 16, but we're off by 4 and 40. And the prior perimeter is 3, and then we add the length of that is 4. 2, 6, okay. Let me add our coordinate. Go to Y. Might be there. We can just figure out the count. We'll be golden. Okay, so it's 0, 0. We get nothing, nothing. Makes sense. Right, it'll be the two ones outside the bounds here. So that should have a perimeter of 2. Okay. 1, 0 here. I should have just 1 out of bounds. All these other R's are within our region, so they're fine. So we add 1 to our perimeter. 3, 0. 3, 0 should have... 0, 1, 2, 3. Okay. Sorry, 0, 0, 1, 0. 2, 0 also has nothing. 1, and then 3, 0. 3, 0 should have 2. It does. Nothing, and 4, 0, I. Perimeter 2. Next one. 3, 1. That's here. Should have just 1. And it does. Just I. 4, 1. That's right. Okay, 3, 2. Should be right there. That one should have just 1 to the south of it. Okay, 3, 3. Perfect. 4, 2. Here. We have 3. Just I, just C, just C. Yeah, that seems right. So that should have a perimeter of 3 on that one. Okay, that's 8, okay. Two, 2. Right there, should have just 1. Does, it's a V, that's right. 2, 3. There, should have 2. 3, should have 3. 1, 2, 3, it does. Okay. Then, oops, da, da, da. What did I do? And where are we? 2 1 2 2 4 3. Come on. Yeah. So almost there. Let's see. 4 2 2 2 2 3 2 3. All right. 2 1. You have 0. That's correct. One. Should have just one of the, yeah. Oh, okay. We're visiting some of these again. We're visiting these twice. Some of these twice. Okay, so it's not quite right. Okay, that's what's happening. So in our perimeter count, no, in our fill, cat maybes, M's. Y's our stack. This unvisited internal cell working for us here. Well, we should be visiting 0, 0 again, and we start with 0, 0. So I'm wondering, I think maybe we need to put X in there. There we go, 216. That's our target number. Okay, let's get rid of the debugging. I think we got it. Bring back this. Okay. If we don't get the answer on this one, I'm afraid that's going to have to be it. And I'm going to have to say the ending. But hopefully we got it. Let's see. Survey says. $19.30, that's what we wanted for the sample input, right? Yep. Okay, so let's change it over to using the actual input. This is why I need to reorganize or rejigger how I structure my Advent executables. So I don't have to recompile just to try different test input. It's super easy enough to actually do it the way it is, but anyway. Yeah, let's go. Super fast even on our big input. Nice. Hey, bang. We got it. What a great way to end the stream. I was worried there for a second. I was like, I don't know. I don't know. But we got it. Okay. So we're probably going to have a little twist on that. Figure out different totals and different shapes and stuff, whatever. But that's it. Okay, thanks for watching. I'm going to just put this code up there. And we're going to call it an end of the year. It's been a great year on the stream, gotta say. We got a lot of projects under our belt here if you have just started tuning in and just watching. We've done a couple of games this year. What else? Some libraries, working on wave function collapse and stuff. It's been good times. Good times. Should have like a highlight reel or something. Okay, input all that. Input all that. Okay, staged, good. 2024, day 12, part 1. Boom. Push it up. And there we go. Probably don't care, but maybe if you do and you want to follow along with me. I'm Agent Ultra on GitHub. This has been Advent of Code 2024, day 12. This is the repository here, where you can see all my solutions and whatnot. If you want to follow me on the socials, I'm on the Fediverse at types.pl. The types.pl server. Web Agent Ultra. That's me as well there. I'm also agentultra.com and various other places. And you can find all my links to all my stuff, including my YouTube channel where I back up the VODs for all my streams. So if you really want to dig back in there and see what we got going on, check it out there. And give us a follow, because sometimes, you know, I do surprise streams and who knows. I got some time off at the end of this year, so maybe we'll do some hacking and follow up and do some more Advent puzzles together. Before the year's end. We'll see. However, that's all the stuff there. Give us a follow here or a subscribe and a like and all that stuff on YouTube as well. Really helps out and lets me know that people are watching and we should still do this. So I usually do these streams once a week on Tuesday evenings about 10 after 8 in the evening, although I'll be on vacation until the new year. So you won't see me until probably after the 4th or 5th or so. And that's all I got for now. Let's just call it there. May you have a wonderful new year, and may your year hasn't been going well. Hopefully it's going to get better soon. And that 2025 is going to be a smashing success. Take it easy out there. May all your monads be free and your types always check. I will see you next time.